Model-based systems engineering is a holistic approach to product design based on the definition of requirements. All design and analysis steps target the requirements, which are also used to validate the final design. Maintaining traceability between requirements, analysis, and verification, through the digital thread, enables continuous performance targeting. It greatly simplifies the process for reviewing and modifying designs, or even reacting to changes in the original requirements. In this video we will see the end-to-end process from defining requirements in the systems engineering environment, to launching a multi-domain design exploration study to target those requirements, all using Siemens tools. The first step in this process is to allocate requirements defined in Teamcenter to the relevant system component. Here we see this done in the Teamcenter system modeling environment using drag and drop from the integrated Teamcenter browser. Ed, the systems engineer, has now built out the component further, linking other requirements and defining design parameters and ranges. This provides a holistic systems engineering view, and we can see that a number of design parameters are needed to describe the brake discs as the outputs. Some analysis is needed to select the brake disc characteristics, so Ed selects the relevant system parts and the requirements being targeted and creates a new optimization study to explore the possibilities. Ed sets out the scope of the study by selecting the parameters he wishes to vary, reviewing ranges and resolution, and focusing on the geometry of the cooling channels. In this step, Ed uses the requirements to set objectives and constraints of the study. This allows rotor temperature, braking distance, and system cost to be minimized, while meeting the requirements on all three parameters. With the optimization study defined, he passes it to his colleague Sam, a simulation engineer, via a workflow in Teamcenter. This ensures that Sam has all the data she needs to build the study, while also providing traceability for other stakeholders. Sam opens her task from the Teamcenter homepage and familiarizes herself with the task. System architecture, requirements, parameters, and verification activities are all connected. By reviewing the associated diagrams, she understands which simulation models are needed to explore and verify performance of the braking system. After a final review of the study parameters, she opens the SimCenter MDAO environment directly from Teamcenter to begin setting up the analysis workflow. The study parameters are automatically passed to SimCenter and identified as variables and responses. Sam adds a simulation step using SimCenter, using a parameterized 3D thermal model of the rotor and caliper. The model is automatically inspected, and input and output parameters extracted. The next step is to connect these to the study parameters and responses. She searches for the relevant values in the simulation model, and tags them accordingly. To calculate the overall cost, she adds a second step to the workflow, using an Excel spreadsheet. This function takes the mass calculated by SimCenter, and computes a cost metric, which is also included in the study responses. Once fully set up, the MDAO project is saved back to Teamcenter. Next, Ed will execute the optimization study created by Sam and review the simulation results. He runs the study interactively, which provides him with continuous feedback on progress. SimCenter's intelligent optimization algorithm explores many different designs to learn the relationships between variables and responses, while driving towards the study objectives. Back in Teamcenter, Ed can immediately see that the best design found provides output parameters which are all within their targeted ranges, and these are automatically verified against the requirements originally defined. A benefit of this fully integrated and traceable approach is that input and output parameters are tied to a particular design revision. If any changes are made elsewhere in the design which impact on this component, it is fast and easy to repeat the analysis and optimization with updated data. In this case, the product cost requirement is reduced from $6 to $4.50. This is below the cost of the current design, so the optimization study needs to be repeated to find an alternative design candidate which is cheaper to produce. Once the requirement is changed, it is flagged as unsynchronized in the optimization study. Ed synchronizes the requirement and parameter and looks for cheaper design candidates by expanding the parameter ranges used in the optimization step, based on insight gained from the previous design iteration. Now the second optimization can be executed by reusing the existing study setup. Ed launches the study for a second time, and now we see the optimizer following a different path to find designs meeting the updated, more stringent, requirements. Back in the system modeling environment, Ed uses the integrated Teamcenter viewer to access the latest optimization study and the resulting design parameters. This information and the status of the verification is visible to all stakeholders. In this case, all requirements were passed by the design selected. Ed returns to the system model and synchronizes the design parameters with the latest verified values. His model is now up to date. In this workflow, we have seen how design, analysis, and performance targeting can be conducted in a joined-up way using MBSE. Central to this methodology is Teamcenter, maintaining full traceability of inputs and outputs, revisions, and verification status at each step, and orchestrating the modeling and simulation tools, shown in this case with the SimCenter portfolio of simulation and test solutions. Thanks for watching. For more information, visit our website.